This is Ref, Brown University physics grad student. Today I'm going to show you how to simulate a black hole. Now, I can't do it in just one video because this is a pretty difficult topic, but in today's video, in today's lecture, we're going to lay the theoretical framework for how to simulate a particle orbiting a Schwarzschild black hole. A Schwarzschild black hole is a black hole that does not spin, that does not rotate, that does not have any angular momentum. So today I'm going to lay the physics, the foundations for simulating geodesics around a Schwarzschild black hole. And then in the next few videos, we're going to see how to simulate a circular orbit, and then an elliptical precessing orbit, and then a hyperbolic or parabolic orbit around a black hole. Let's get started. The first equation that you must know for a black hole is the Schwarzschild metric. So let's write down the Schwarzschild metric. The Schwarzschild metric tells us how big a small step in space-time, ds squared, is around a black hole. So this is given by minus 1 minus 2m over r dt squared plus 1 minus 2m over r to the negative 1 dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. Now, if you're wondering where this long equation comes from, I've explained it in previous lectures, so go check those out. But essentially, this equation is a solution to Einstein's field equations. So Einstein's field equation is the big result of Einstein's 10-year quest to understand gravity. So Einstein's field equation looks as follows: G mu nu, the Einstein tensor, plus the cosmological constant, times the metric, is equal to 8 pi times Newton's gravitational constant over c to the fourth times T mu nu. And so this equation was for a long time thought to be unsolvable. And by long time, I mean about 6 months. After 6 months of Einstein publishing this equation in the Annals of Physics, Carl Schwarzschild found a solution for G mu nu. Carl Schwarzschild found a metric, G mu nu, that would solve the Einstein field equation, this one. And the metric he found was the Schwarzschild metric, the metric describing a black hole. If you're not sure what a metric is simply like a ruler. A metric is just like a ruler that tells you how space and time bend around a black hole. So you can see the first term of the metric describes how time slows down around a black hole. The second term describes how radial components, how a ruler would stretch near a black hole. And the third and fourth terms describe how angular coordinates stretch around a black hole, those theta and phi terms. So if you want a deeper intuition for the Schwarzschild metric, I suggest you check out my other lectures on the Schwarzschild metric. So now let's go ahead and use the Schwarzschild metric to write down the equations for a particle moving in a geodesic around a black hole. So here's our black hole. Our black hole has some mass capital M. It has some Schwarzschild radius r sub s. And what we'd like to do is write down the equations of motion for a particle that's orbiting our black hole. So here's a particle. Maybe it has a mass lowercase m, and it's orbiting the black hole as follows. Okay? We'd like to know what are the equations of motion for this particle. So what I'm going to do is write down the Hamiltonian formalism for this particle. So the Hamilton equations of motion say that the total energy of this particle is kinetic energy, let's write that as K, plus potential energy. Now the kinetic energy we can simply write as P squared over 2m. The potential energy is actually contained in the metric. That's the potential energy created by the gravitational field of the black hole. So P squared over 2m is just another way of writing 1/2 mv squared. It's just the kinetic energy of our particle. Now if our particle has a unit mass, meaning that our particle only has a mass of 1, then this m becomes 1, this m becomes 1, and so we simply have a total energy of P squared over 2. Now, where does the black hole come in to the particle's energy? Where is the black hole in this total energy? Well, we can write P squared as P mu in general relativity. Okay, p mu is the same thing as p squared. And then we can lower this contravariant momentum 4 vector by bringing in the metric g mu times p mu squared divided by 2. And now I'm going to expand this out into its 4 terms. So this is going to be g t t p t squared plus g r r p sub r squared plus g theta theta p sub theta squared plus g phi phi p sub phi squared. All of this times 1/2. Okay, so that's all good and nice. Now let's write down the momentum 4 vector components for our particle. So for our particle of mass m here, it has some kind of a momentum vector, p mu, that describes our particle's momentum. So what are the components of this momentum 4 vector? Well, this momentum 4 vector has a time component, p sub 0, or as I wrote over there, p sub t. So let's stick with the convention. And it has spatial coordinates, p sub r, p sub theta, p sub phi. What are each of these components? Well, the p sub t component is actually just the energy. It's the negative energy of the particle. And in fact, I can write that in a more expressive way. If we define the effective energy of the particle as E tilde, then this is P sub T divided by M, okay? For P sub R, we can just write that P sub R is equal to dr d tau. If we're simulating a circular orbit, the orbit doesn't change, the radius of the orbit doesn't change, so P sub R is 0. P sub theta is simply d theta d tau, and that's also 0 if theta is fixed at the equator. What do I mean by fixed at the equator? Well, if we have our black hole, let's say, is that too far? Maybe you won't see. Let's say we have our black hole here. Here is the equatorial plane surrounding the black hole. So this is the equatorial plane surrounding the black hole. And this plane is represented by theta is pi over 2. Okay? So if we choose theta to be fixed at pi over 2, that means our particle is going to be orbiting the black hole on this plane, pi over 2. So it's never going to leave the plane. And so that means P sub theta, the momentum in the theta direction, is simply going to be 0 since theta doesn't change. And finally, if we're looking at the last momentum component, what's P sub phi? Well, let's define the angular momentum of our particle, J tilde, to be P sub phi divided by M. So that means P sub phi is simply M times J tilde. So we have all of the components for our momentum 4 vector, and now we can just plug it in to get the Hamiltonian for our particle. So H, the Hamiltonian for our particle, is 1/2, and then we're going to expand out in terms of the metric. So GTT is the inverse of this, so -1 minus 2m over r to the -1, okay? P sub t squared, so let's just write P sub t squared, or actually, yeah, let's, I don't know if whether or not to write it right now. Let's write it as just P sub t squared, plus G sub rr, which is the inverse of this, 1 minus 2m over r, times P sub r squared, plus I have r squared, so r squared, P sub theta squared, okay? And finally, plus r squared. Now this should be r to the -2 because we're taking the inverse metric, and r to the -2 sine -2 of theta, P sub phi squared. Okay, this is all great. Now let's make some simplifying assumptions. If we have a circular orbit around the equator, then P sub r is 0. This is 0. P sub theta, as we said, does not change. This is 0. And sine of theta is sine of pi over 2, which is simply 1. And now we've made a lot of simplifications. So our Hamiltonian is going to reduce quite a bit. So our reduced Hamiltonian H is now 1/2 times -1 minus 2m over r to the -1 times P sub t squared plus simply this component, r to the negative 2 times p sub phi squared. Now, what can we do with this Hamiltonian? We can find the equations of motion for our particle. How so? Well, we just use Hamilton's equations of motion. So Hamilton's equations of motion can be written in matrix form as follows. H is equal to L grad E. So what do I mean by that? H is simply, in this case, it's going to be the time derivative with respect to proper time of each one of our state vector variables. So here are our variables. We have t, r, theta, phi, and hopefully you can still see this. P sub t, how low can I go? Okay, pretty low. P sub r, P sub theta, and P sub phi. Wow, that is very low. Maybe you're not able to see that, but in any case, these are the 8 variables that comprise our state vector, and their time derivatives are with respect to proper time, the proper time of our particle. And this is going to equal the following matrix. So we're going to have zeros along this diagonal, and we'll have a kind of inverse version of the identity matrix. We'll have ones here, negative ones here, and then here we'll simply have t, r, or rather we'll have the gradient of the energy. So that means we'll have partial h, partial t, partial h, partial r, partial h, partial theta, partial h, partial phi, and I'm just going to keep going. Hopefully, oh no, you can't even see that. That's just sad. Okay, maybe I'll rein it in over here. So this is going to be 1, 0. So now we're going to put this down. So this is partial h, partial t, partial h, partial r, partial h, partial theta, partial h, partial phi, partial h, partial p sub t, okay, partial h, partial p sub r, partial h, partial p sub theta, partial h, partial p sub phi. Okay, finally. All right, now a lot of these derivatives are actually very easy because the Hamiltonian does not depend on many of these things. So notice the Hamiltonian has no dependence on p sub r or p sub theta. So immediately this is 0 and this is 0. Okay, so that's good. That is good. Do we see any temporal dependence on the Hamiltonian? Well, I'll reserve that for later. Okay. Actually, let's see. Partial h, partial t. No, I don't see that. So this should also be 0. So that should imply the conservation of energy. Now there is the Hamiltonian does depend on r, and it does not depend on theta. So it seems like this is also good to go. It does not depend on phi either. So wow, this is either suspicious or sad, but or gratifying if you're looking for simplifications. It depends on p sub t, it depends on p sub phi, it depends on r. So let's see how those evaluate out. So we have partial h, partial r. Let's do that first. So that's going to hit this component and this component. So I'm going to have 1/2 and then bring out the -1. So that gives me 1 to the 2m over r to the -2. And then here, this will give me, this is r to the -1. But this is going to become 2m over r squared. Okay, so that should be good. 2m r to the -1 becomes the -1 takes this to a plus. Good. So this is good. And then I have p sub t squared unaffected. And let's look at the derivative of this with respect to r. That's going to be -2r minus 3 p sub phi squared. Okay, that's great. And we know what p sub phi is in terms of m and j tilde. So all of this is done. What about partial h, partial p sub t? So partial h, partial p sub t. That's going to be hitting this variable here. So I'll just have 2 coming out. And so this is just fairly easy. This is just -1 minus 2m over r to the -1 times p sub t. Okay, so that is good. Okay, and what else do we have? Partial h, partial p sub phi. Partial h, partial p sub phi. Now that hits only this component here, so that's going to give me r to the negative 2 times p sub phi. Okay, so now we have everything we need for the equations of motion. So let's write out what the actual equations of motion are for our particle. I'm going to take out, let's take this out. Okay, so take all of this out, and here we go. Okay, so if I write down my Hamiltonian, so H is equal to L grad E, so let's write down just our state vector time derivative. So T dot, R dot, theta dot, phi dot, P sub T dot, and I wish I used red, P sub R dot, P sub theta dot, and P sub phi dot. Okay, so all of these are equal to, now let me use red. So let's see, if I want to find, let's write down the full matrix. So I'll have 0, 0, 0, 1, 0, 0, 0. So it should be 8 by 8, 1, 2, 3, 4, 5, 6, 7, 8. Okay, I believe that should be right. Or maybe this should be 0, this should be 1. 0, 0, 0, 0, 0, 1. Okay, looking good so far. And let me just make sure that I'm doing it right with a sample size. So Q dot P dot should be 0, 1, minus 1, 0 times Q times P. So let's see if that holds up. So that means Q dot is equal to, or partial H, partial Q, I mean, and partial H, partial P. So Q dot is equal to partial H, partial P, and that is correct. I know that. And P dot is equal to minus partial H, partial P. Whoop, that's not quite right. P dot, hang on. Okay, this should have said Q dot is, wait a second. Okay, Q dot is this. Okay, good. And this is Q here. Okay, good. So this is correct. So let's just keep going here. Extrapolate this to an 8 by 8 matrix. So these are just Hamiltonian equations of motion. Okay, that's my identity on the upper right. And I'm going to put an anti-identity on the lower left. So here we go. Minus 1, 0, 0, 0, 0, 0. Minus 1, 0, 0, 0, 0, 0. And minus 1, 0, 0, 0, 0. Okay, so this is my whole matrix. And now I'm going to multiply it with the gradient of my energy vector. So that's going to be as follows. So partial H, partial T is 0. I have partial H, partial R, which is this long mess. So let me just write it as this. I have 0, I have 0. I have partial H, partial T, or partial P sub T rather. And then I have double 0, then partial P sub phi of H. Good, very good. Okay, so now we're going to write down the equations of motion for each one of the state variables. So let's do that. So let's pick a color. So T dot, first let's start off with T dot. So T dot is this. This is going to be this 1, and this 1 acts on the 5th element. So 0, 1, 2, 3, well, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So that means T dot is going to be partial P sub T times H of H. Okay, what about R dot? R dot is going to be the next one down, which is just 0, which makes sense. The radius should not change. The theta dot, what's theta dot? Again, theta dot should not change if we're staying fixed at pi over 2. And indeed, we see that this one hits the 0, that gives us 0. And phi dot, now phi dot should change, but at a constant rate. So phi dot has this 1 attacking this. So we have partial p sub phi of h. Wonderful. So this is how our 4 state vectors for coordinates change. Now how do the state vectors for momenta change? So p sub t dot, okay, so energy is conserved, so this should be 0. So we have -1 hitting this 0 gives us 0. Wonderful, that means energy is conserved because p sub t is just minus e. How about p sub r? Again, this should be 0 because the radius is not changing. But let's see, p sub r dot is going to be this, which acts actually on partial h partial r, which is maybe a little bit worrying, but that's what the math gives us. P sub theta dot is going to be p theta. So this -1 acts on this 0. Okay, that makes sense that the theta component is not changing. Okay, remember, what is p sub theta? It's just another way to write partial p theta partial tau. So it's like a second derivative of the theta vector. So this is u theta partial tau divided by n. Okay, good. Anyway, so this is all been there, done that. So p sub theta dot is 0. Maybe that should be fine. And finally, p sub phi dot, what is that? That is this element, which is -1, and that hits this 0. So we should have only 3 non-zero terms, and indeed that's what we have. T dot, phi dot, and p sub r dot. Funnily enough, p sub r dot should be, oh, p sub r is 0, but maybe p sub r dot is not 0. Okay, yeah, okay, good. So now I'm going to plug in, based on what we derived before, plug in for these values here, and find out what the final equations of motion for each one of these state variables are. So erase all of these and let's write them down. So we're going to have t dot, so t dot is equal to partial h partial p sub t, which is this. So -1 minus 2m over r to the -1 times p sub t. Okay, that's t dot. And phi dot, which is the only other non-trivial coordinate that changes, is, where's phi dot? Partial h partial p sub phi. That's r to the -2 p sub phi. Okay, very good. So this is how all of our state vectors change. Very good. So I'm going to box this in. Okay. Box this in. Okay, that's t dot, phi dot. We have our r dot here. We have theta dot here. Okay, we're going to put them into a computer shortly, but this is how our coordinates change. Now, how do our momenta change? Well, there's only one momenta that changes, which is p sub r dot, and that changes according to this, partial h partial r, and that is going to be 1/2 times, let's see, 1 minus 2m over r to the -2 times 2m over r squared times p sub t squared minus 2r to the -3 p sub phi squared. Okay, so these are the only 3 non-zero components of the state vector that change. Okay, very good. Now I'm going to pause here for questions. Just kidding, I know you can't ask me through the screen, but let's just box everything we have. So we have our 4 coordinate state vectors and how they change, and p sub theta is 0, p sub theta dot is 0, p sub phi dot is 0, and p sub t dot is also 0. So everything is 0. Okay, so very good. Now we just have to plug these into a computer and put the correct initial conditions for a circular orbit. That will be the subject of the next video. Thanks for watching. We'll see you in the next one.